All right, let's move on to our next thing. So we're getting into the second part of today, where we are starting to look at rates of change and different ways that we can calculate those rates of change. And so what we want to look at is a couple of different ideas here. So one of the ideas that we want to look at is that, let's just say that we are looking at a reaction that has reactant A turning into product B. And let's just assume that that is the correct and balanced form of that reaction. Well, what we can monitor over time is, through different kinds of techniques, we could look at, well, how does the concentration of the reactant change as we go through the reaction? Take, for example, spectrophotometry. We could monitor the change in color over time and figure out, okay, the reactant is disappearing. Or we could look at the rate of change of a different color and note how the product is appearing. But what we would find is that if this is our stoichiometry, where we've got a one-to-one conversion of reactant into product, what we're going to see is that the rate of disappearance of the reactant is going to be equal and opposite to the rate of appearance of the product. They're going to be equal and opposite rates. And that is why we would have a negative sign over here. Since the concentration of the reactant is decreasing, that rate would be one that is lowering over time. To make it equal to the product, we would show that it is the opposite sign, so that the negatives would cancel and give us a positive. Now we can measure this change in concentration a number of different ways. One of the ways that we can measure that rate of change is through something called the average reaction rate. And all that we do to calculate the average reaction rate is we pick 2 points on the graph and we monitor the change in concentration divided by the change in time. So if I wanted to look at the rate of change for this product, I could pick 2 different times on the mark, and doing just a bit of estimating here, 0.075, 0.125, the change in molarity would be final minus initial. And the change in time would be final minus initial as well, 0.6 seconds minus 0.2 seconds. So I would have 0.05 molar over 0.4 seconds. And if I do a little bit of quick math here, 0.05 divided by 0.4, I get 0.125 molar per second. So over that time interval, the average rate of change was about 1/8 of a molar per second, 0.125. And we could do this for any part of that reaction curve. Pick any 2 points, take the average rate. So that's one way of measuring. But one thing that we'll notice about that is that we can clearly see that these reactions proceed at different rates at different times. the slope of the reaction at the beginning is far steeper, far faster than the slope of the reaction toward the end. And so an average reaction rate might not give us a really great and accurate picture of what's going on inside the reaction itself. So there might be other things that we want to look at. But let's stick with average here for a second. Let's expand our chemical reaction to something that's a little bit bigger and a little bit broader. So if I have the balanced chemical reaction, A plus B makes C plus D, where A, B, C, and D all have different stoichiometric coefficients, or even if they have the same stoichiometric coefficients, I can equate all of their average rates by looking at two things. First, are they reactant or product? If they're reactant, then we put a negative in front. If they're product, then we just keep it as positive. But the rate of change is going to be influenced by one other factor, the stoichiometry. Let's just put some perspective on this. Let's make this a little bit less generic, a little bit more detailed. Let's say that I have 3A reacting with 2B to make C and 5D. Just for the sake of argument here. Which reactant is going to disappear at a faster rate, A or B? Well, let's look at the stoichiometry. In this reaction, 3 molecules of A are reacting with 2 molecules of B. If I have 50 molecules of each, which one's going to run out faster? It's going to be the A, because I'm using 3 A's every time the reaction runs. Or as I'm only using 2 B's. Which product is going to appear at a faster rate, C or D? Again, look at the stoichiometry. Every reaction run generates 1 C but 5 D's. So the greater my stoichiometry is for a given part of the reaction, the faster that product or reactant is going to appear for products or disappear for reactants. Now, the point of this equation down here is to make them so that they are all on equal footing. And that's why if I'm putting them all on equal footing, if I'm going to put them all in the context of C, which only has 1, then I need to take that D and cut it down by a factor of 5, multiply it by 1/5. That way C and D are on the same terms now. And I would take A and B, and I would cut A down by 1/3 and B down by 1/2, so that would match the stoichiometry of C. And so that's what these fractions are all about. So if I know the rate of change for the reaction, I can use that rate of change to figure out what is the rate of appearance of A, or what is the rate of, the rate of disappearance of A, or what is the rate of disappearance of B, or what is the rate of appearance of D. And it all comes down to the stoichiometry. So when we're evaluating reactions, the higher the coefficient is, the faster we're going to see that particular reaction species change. So if it's a reactant, we're going to see it disappear faster. If it's a product, we're going to see it appear faster. But this system of fractions helps us to kind of standardize everything so that we could compare them all evenly and put them all on the same terms. So if I wanted to know the rate of the reaction itself, I would put it down to a unit of 1, which is why I would take that D term and multiply it by a fifth. Multiplying it by a fifth takes the 5 and turns it into a 1. For C, I wouldn't need to do anything because it's already singular. It's already 1. All right, let's break into another top hat question here. All right, you've got to do 2 things. First, you have to balance this equation. And then once you have it balanced, figure out which reactant or product is going to, figure out which product is going to be produced slowest. So first balance it, then figure out what is going to be produced more slowly. If you are struggling with the balancing part of this, what you should kind of come to grips with is, as far as the carbon and the nitrogen goes, they are already balanced in this form. The hydrogen and oxygen is not. So best practice here would be to try to figure out how to balance the hydrogen and hope that the oxygen comes out along the way. So right now there are only 5 hydrogens. We need 9. So if we make this 3 waters instead of just 1, that would give us the 9 that we were hoping for. Now that would pose a problem for the oxygen as well, because now we have oxygen in even and odd. If you remember back to 105, what we do in this situation, the easiest thing to do is double everything. So if we double 2, 2, and then to balance this would have been 3 over 2, so we'll just turn it into 3. Two, and now 3 turns into a 6. So I now have 6 carbons and 12 plus 6 for 18 hydrogens. I have 2 nitrogens and 6 oxygens. And on the product side, I have 6 carbons now I have 6 plus 12 for 18 hydrogens, 2 nitrogens, 6 oxygens. There's my balance. So now that the equation is balanced, we've got to figure out which product is going to be formed slower. Is it going to be the carbon product or the water? And we've arrived at the correct answer. So the carbon-based product is going to be the one that is going to react more slowly because its stoichiometry is lower. So the water is going to form about 3 times faster than the carbon product would have. All right, let's look at another. So considering this reaction, we've got nitrogen dioxide decomposing into nitrogen monoxide and oxygen. We're told that over a time range, the rate of formation of oxygen is 4.3 times 10 to the negative 6th molar per second. What is the rate of consumption of disappearance for nitrogen dioxide over that same time period? You are probably going to have to use scientific notation. Make sure that you use the capital E to input that instead of trying to type in the times 10 to the. So really what we're going after here, what is the relationship between the rate of formation of oxygen and the rate of disappearance of the nitrogen dioxide? Since there is a direct relationship between the rates of reaction and stoichiometry, the easiest way to answer questions like this is actually just doing it stoichiometrically, thinking of it like a conversion. And so the easiest way to do that would be if I look at this as, converting oxygen into nitrogen dioxide. I know that for every oxygen, I would get 2 nitrogen dioxides. The rate of disappearance of the nitrogen dioxide would just be double the rate of appearance of oxygen. And the same would be true for the nitrogen monoxide product as well. It would appear at twice the rate that the oxygen appeared. So the business on the previous slides about the fractions and whatnot, that's what we use to calculate the rate of reaction for the overall reaction. But if we are just comparing one reactant to another or one product to another, we can use simple stoichiometry to do that. All right. Questions with either of these two kinds of problems? This is the majority of the stuff that you're going to see in tonight's homework assignment. Is just doing these kinds of conversions. Okay, so as I was saying before, one of the problems with average rates is that average rates do change over time. We can see that as we go from the beginning of the reaction onward, the reaction is fastest at the beginning and it slows down over time. Reaction is faster here than it was as we go down. And so if I'm looking at average rates, they can be a little bit confusing because we have to answer the question, well, When are we talking about? Over what time period? And so one way that we can try to quantify that a little more precisely is using something called an instantaneous rate of reaction. And that's what these actually are. These are instantaneous rates of reaction. They are found by calculating the tangent, the slope of the tangent line at the different points of the curve. And so if you're ever curious about when is that calculus I've been studying going to get used, this is one of the applications of that calculus. Now, luckily for you, you're not going to be asked to do the actual calculations of these tangents, but that is where they are coming from. And so one of the things that will get kind of discussed here is, okay, we can probably understand that an instantaneous rate is a better way of expressing the rate of reaction than the average, because an average is going to focus on too broad of a window of time, and it's not going to give us a whole lot of good information. Instantaneous rates do give us a little bit better information because they give us more of an exact kind of bullet point. But again, we're still going to run into the problem of, well, when do we actually view that instantaneous rate? And what we're going to get into tomorrow is we're going to actually look at instantaneous rates here at the very moment where the reaction begins. Now, why here? Because at that moment, the reaction is actually going to proceed the most quickly. And so if we can measure that instantaneous rate, we're going to have a pretty good insight as to when the reaction is going to proceed the most quickly and what kind of information we can actually get from that. And where that's going to lead us is to something called a rate law. And so we're going to spend most of tomorrow talking about rate laws, but I'm going to kind of set the table for that here now. So again, this moment right here, where we have the highest concentration of reactant, the fewest concentration of products, the least interference possible, this is when the reaction is going to proceed the most quickly. And all reactions, regardless of their speed, eventually hit a kind of plateau where they don't stop reacting, but they definitely slow down to the point where we either can't notice a difference or they've proceeded to such a far point to the products that we just don't have anything measurable to measure anymore. Rate laws are a way that we can start to quantify the relationship between concentration and reaction rate. And rate laws take on this general form where we are looking at the rate of reaction and equating that to two factors. Well, two general factors. One, the rate constant, K, and the second major factor is the concentration and order of the reactants. Concentration given to us by the value in brackets, order given to us by the exponents that go along with those concentrations. So rate laws are impacted by two things. They're impacted by the rate constant, and the rate constant is, as you can expect, a constant value, provided that we are under similar kinds of conditions. So what I mean by that is similar temperature, similar pressure, those kinds of external environmental factors. If we keep that kind of stuff consistent, the rate constant is just that, it's a constant. If we start to change temperatures, then we're going to see that we get a different rate constant at different temperatures. And that's part of what Monday's lecture is going to be all about is, well, what happens when we change that temperature? The other part is going to be the focus of tomorrow. The idea of this relationship between reactants and the rate, and what the role of those exponents are, and how we find out what those exponents are. So, like I said, K is the rate constant. The rate constant is always a positive value. The values in brackets are concentrations. We're only going to focus on reactants here. If you were to study kinetics at a higher level, at the PChem or graduate school level, the rate laws get a little bit more complicated, but we're going to keep it relatively simple and look just at reactants. And then the exponents are what are called the orders of reaction. And orders give us a relationship value between what the reactant is and what the rate is. And we referred to them in ordinal terms. First order, second order, zero order, and so on. So what do those orders tell us? Well, they give us a direct relationship kind of quantification. If we say that something is zero order, what that means is that that reactant's concentration actually has no impact whatsoever on the rate of reaction. Now, it still participates in the reaction itself, but we can't get the reaction to go faster by increasing its concentration. It doesn't have that kind of impact on the kinetics. When we describe a reactant as being first order, what I want you to think about is a linear relationship. And what I mean by that is if we double the concentration of that reactant, we would expect that the reaction speed would double as well. If we triple it, we would expect the speed to triple. If we cut it in half, we would expect the speed to be cut in half as well. It would take twice as long. So zero order has no impact. First order, it's a linear relationship. Second order, it is an exponential relationship. And what we mean by that is we are going to square the impact. So if I triple the concentration, the reaction is going to go 9 times faster, 3 squared faster. If I quadruple it, it's going to go 16 times faster, 4 squared. If I cut the concentration in half, it's going to go 1/4 of the speed, 4 times slower. So second order reactants have the greatest impact. Now, one other thing that we're going to talk about tomorrow is something called the overall order of reaction. And the overall order of reaction is the sum of all of the individual orders. So if I have something that is 0 order and first order and second order, then the total order would be 3, 0 plus 1 plus 2. Right, and this is where we're going to stop for today.